Sensors for measuring acceleration, pressure, level in a tank. They are often made out of more than just one component. Often in combination with some mechanical system with spring and some mechanics for transferring motion and levels, whatever. I mean, it makes them more complex, just make them a little bit like more complex than just a resistive sensor. So this is what I'm going to show you now. So we are talking about sensors for acceleration, for pressure of gas or liquids, and sensors for tank level. We can start with acceleration. And in this simple sketch that you see here, it's like a toy car, and we have a reference mass here on this green thing here that is assembled on a small spring that is attached to the wagon. And then when the wagon starts to accelerate in this direction, then there will be a force on this mass in this direction that is equal to the mass multiplied with the acceleration. These are well known from physics, classical physics courses. And when you have a bending on this metal sheet spring, then if you assemble on one side a strain gauge sensor and another strain gauge sensor on the other side, then you will have compression on one side and you will have a pulling force on the other side. Like you can see here on this sketch here. So there will be stretch on one side and there will be compression on the other side, which allow these two resistive sensors to be connected in a half bridge, and you can sense the acceleration output as a voltage. And these kind of sensors, they are used, for instance, in cars for measuring collision forces to fire off the airbag system in the car in case of an accident. Here is another example of the same acceleration sensor, but in this case we are using a piezoelectric crystal. And the piezoelectric crystal here is preloaded with a force from the spring that we see here inside this chamber. This is the sensing axis, and whenever there is an acceleration in any direction, then the force on the piezoelectric crystal will change, which then will generate a charge on the input of this charge sensitive amplifier that can be sensed as a voltage on the output. And the spring preloads the mass with a force such that acceleration can then be sensed like in both directions. This is a pressure sensor, so it's a reference chamber with a connection on both sides. This is for one pressure, P2, and this is for another pressure, P1. Then you have this piston that is possible to move in either direction inside this chamber, and this piston is also mechanically connected to the spring, so the force that arises from the pressure difference here between P2 and P1, that force on the piston is also balanced by the force on the spring. And in the same way as previous acceleration sensor, we have assembled two strain gauge sensors on each side on the spring, so that you can have a stretch on one side and compression on the other side, which allow us to connect these two strain gauge sensors in a half bridge and get the voltage output of this bridge that will be corresponding to the pressure difference between P2 and P1. This is a level sensor that can be used for a tank, a kind of classical one using this float. So when we are increasing or decreasing the level of liquid in this tank, then the float is moving upwards or downwards. And it is connected to the kernel inside this differential transformer. So the position of the kernel will change, and you will have a corresponding change on the output voltage from the differential transformer. This arrangement can be used to measure the level of liquid in a tank. Another kind of sensor, a capacitive sensor for measuring the liquid of a tank. The benefit of this one compared to the previous one is that in this case you don't have any kind of parts that are moving. So it's only a capacitor that you are lowering down into the liquid. And the principle here is based on the theory of a simple plate capacitors, where the capacitance of this capacitor is equal to the electrical constant multiplied with the area of the plates divided by the distance between those plates. And then for the tank we can divide the part of the plates that are above the level of the liquid and the part that are below the level of the liquid. So the total capacitance is equal to the C0 plus CL, where CL is the capacitance where the plates are in the liquid. And we will have different the electrical constants for air as we have in the water. So epsilon 0 is for the air and epsilon L is for the liquid. And in the end we end up at an expression here that shows proportional sensitivity to the height of x of the liquid. Of course then you can also have an output that is proportional to the volume. So this was about the more complex sensors.